In the previous session, we discussed the preliminary requirements for discussing Lyapunov stability. Today, we'll start with the Lyapunov stability criterion. So, what does Lyapunov stability tell us? It basically deals with the concept of motion. So, uh, using the general problem of motion stability, whether a system is moving continuously or it is reaching a steady state value at some point of time, we can define whether a system is stable or not. In other words, as I have been repeatedly saying, a system is described to be stable if starting the system somewhere near its desired operating point implies that it will stay around that point forever. Fine. So the motion uh, stability states that your system will stay at a desired operating point uh, for ever. Fine. Uh, Now, as far as the Lyapunov stability goes, it was introduced back in 1892, but was accepted uh, much later in 1960. Mm, there are two methods by which the Lyapunov stability has been described in literature. One is the indirect method, and second one is the direct method. As far as the indirect method goes, we have both these two methods. They are applicable to both linear as well as nonlinear systems. As far as the indirect method goes, we have already studied it somewhat. Fine, it actually deals with the problem of linearization, deals with the concept of linearization. Using the problem of using linearization, we can state whether a system is stable or not. While as the direct method, it is the more general of the two. It is the actually what Lyapunov um, stability theorem is associated with, and it's important for analysis. Now, this is based upon the energy concept. Or what is also known as the energy function, or the Lyapunov function in this case. So what it actually meant was that a system, when forced, it definitely requires some amount of energy. For a period of time, the system will lose its energy and come to a halt. This, if such a function can be derived, that was known as the energy function, that actually describes this motion, this equation that relates how this energy is lost over a period of time. Using that, we can actually determine whether our system will be stable or not, whether it's coming to a standstill position or not. So there are two methods in case of Lyapunov stability. One is the indirect method, and second one is the direct method. The first one, the indirect method, it's associated with the problem of linearization, and second is the direct method. It's the more general of the two. It's what is actually referred to nowadays as the Lyapunov stability criteria. It's based upon the energy concept, and again, there will be a number of ways of defining the direct method. We'll be seeing to that. So starting with the indirect method. So the indirect method deals with the local. It is concerned with the local stability of a system. So what this local stability basically refers to is that it actually tells us how a system will behave around an equilibrium point, and it will not, how the system will behave on the equilibrium point, it will not give us any information, or will be able to provide us information about stability of a system some way distant away from this equilibrium point. So for example, your initial conditions are away from this equilibrium point. It will not give us the information about the stability of this initial condition of the system. It will be more or less confined to the equilibrium point and give us the stability, or define the stability for the low at the very particular point. Right? So a nonlinear system should behave. What this indirect method basically tells us that a nonlinear system should behave in its stability should be, can be approximated using the linear equivalent of this. So more or less, we can say whether a system will be uh, stable, a nonlinear system will be stable by approximating it to its linear equivalent. So linearization, we have already done that portion. Using the Jacobians, we can find out the linear approximate of the system. While as this will tell us how the system will behave around that equilibrium point only, around which we are trying to find out the stability of the system. So while doing the linearization process that we have done, we have seen that we substitute x dot equal to 0, and for different values of initial condition we will find out different linear approximates. So each and every state will give us the behavior around that very particular equilibrium point. Not, it will not be so if once equilibrium point is stable, it does not mean that another equilibrium point will be stable as well. Fine. So consider a nonlinear system. X dot equal to f of x. Fine. Where x will be x1, x2, x2, vector of system states, and f is here a nonlinear function of f of x of these states. The linear approximate that we have seen will be given by the Jacobian matrix. So linear approximate around the equilibrium point, linear approximate is given by the Jacobian matrix, where A will be defined as delta f divided by delta x for x equal to 0. That is, A is equal to delta f1 by delta x1, delta f1 by delta x2, so on up to delta f1 divided by delta xn, and similarly you can have delta fn divided by delta x1, so on up to delta fn divided by delta xn. So finding out the equilibrium points x dot equal to 0, find out the partial derivatives of these different nonlinear functions with respect to different states of the system. We can find out the A matrix, and therefore our linear system will be given by x dot equal to ax then. Fine. So for a non-autonomous system, as we have seen the case, this x dot will be equal to ax plus bu, where A will now be given by delta f divided by delta x, while x dot x is equal to 0 and u is equal to 0, and B will be given by delta f divided by delta u for x equal to 0, u equal to 0. Delta f divided by delta u for x equal to 0, u equal to 0. Whereas for a autonomous system, this will be simply equal to x dot equal to ax. Fine. So this gives us the linear approximate of our system. So in the indirect method, what we do is we find out the local stability of a system by approximating the nonlinear system as the linear equivalent by approximating the nonlinear system by through its linear approximate, and this will give us the stability at that very particular equilibrium point. So as we have already defined, we can substitute x dot equal to 0 to find out the equilibrium points, and we can find out the values of a and b using the Jacobian matrices. A is given by delta f by delta x, and b is given by delta f divided by delta u. Now, say for example, we have to find out the stability of the system. For example, we have x dot equal to ax plus bx raised to power 5. So let us consider or examine the stability of the system using the Lyapunov indirect method. And for that case, that actually tells us whether for using the Lyapunov indirect method, what we do is we will go for the linearization of the system. So substituting x dot equal to 0, first of all, we can see that ax plus bx5 will be equal to 0, which implies x into a plus bx raised power 4 is equal to 0, which implies x equal to 0 and a plus bx4 equal to 0, which will give us x equal to minus a divided by b, the fourth root of this. Fine. So you have multiple equilibrium points. Focusing on x equal to 0, that is the origin point, we can determine the stability of the system with respect to origin. We will not be determining the stability at different other equilibrium points for now. So for x equal to 0, we have delta f by delta x at x equal to 0 will be given by differentiating delta by delta x of ax plus bx5, which is equal to delta by delta x, that is a plus 5bx4 substituting x equal to 0 here, we'll be left with a only. So that means a is equal to a, that means x dot is equal to a times x. So this is our linear approximate of our system. That was ax plus bx5. We have x dot equal to ax, and so we can easily determine the stability of the system. Say for example, a is less than 0, that means the system will be asymptotically stable. If the eigenvalues are negative, a is less than 0, the system will be asymptotically stable. If a is greater than 0, that means the eigenvalues are positive. This is simple one element matrix. Then the system is unstable. Now if it is equal to 0, we cannot actually tell whether the system is, we will not be saying that the system is marginally stable. We cannot tell whether the system is or is not stable. Fine. So we have this equation x dot equal to ax plus bx raised to power 5. So Lyapunov indirect method, to find out whether this system is stable or not, what we do is in the Lyapunov indirect method we go for the linearization process. Substitute x dot equal to 0, that gives us the equilibrium points of the system. So you'll have different equilibrium points of the system. So for each and every equilibrium point you can determine whether your system is stable or not. We are choosing x equal to 0, the origin point. So linearize the system by finding out the Jacobian, that is the A matrix. So this basically gives us the A matrix, delta by delta x for x equal to 0. We have found a is equal to small a, that means x dot is equal to a into x. So for a less than 0, that is negative value, the system is asymptotically stable. For a greater than 0, the system has positive eigenvalues, therefore unstable. For a equal to 0, uh, we cannot tell whether the system is stable or not. So in another case where x dot equal to bx raised to power 5, linearization, if we have simply x dot equal to bx5, so linearization method will actually fail in that case. So we will not be able to solve, we cannot determine whether the system is stable or not, and we'll have to use the direct method there. Fine. So we are not actually yet gone to the, we are not touched the direct method, we are not stated that yet. Let's take another example. Let's say we have a system x1 dot equal to x2 plus x1 cos of x2, and x2 dot is equal to, so for this example again linearize, so you can actually substitute x1 dot equal to 0 and x2 dot equal to 0, and you can find out the equivalent points of the system. So let's try to linearize this system around the origin. So there will be again number of equivalent points of this system. One of them will be x1 equal to 0, x2 equal to 0. So linearize about the origin, that is x1, x2, 0, 0, being 0, 0. So we have a equal to delta f1 divided by delta x1, delta f1 divided by delta x2, delta f2 divided by delta x1, delta f2 divided by delta x2. So delta f1 divided by delta x1, that means differentiating this with respect to x1, and so this becomes 0, this becomes cos of x2, where cos of x2 will be a constant in this case. Delta f1 divided by delta x2, x2 का 1, cos, differentiation of cos, is minus sine x1 minus sine x2, and delta f2 divided by delta x1, delta f2 divided by delta x1, 0, this is x1 square, that means 2x1 plus x1, that means plus 1, plus sine of x2, and this here is delta f2 divided by delta x2, it's 1 plus x1 cos x2. Fine. So where x1 is equal to 0, x2 equal to 0. So once we substitute these values of x1 equal to 0 and x2 equal to 0, what we'll be getting is a is equal to cos 0, 1 minus 0, that's actually 0, 1, sorry, and we have 2 into 0, 1 plus sine 0, 1 plus sine 0, 1 plus x1 cos x2, 1 again, cos 0 is 1, 1, 1 minus, this is 1 here, this is 1 here. Uh, this was x2 square here. Since this is x2 square, this remains same. This here, only difference here is this becomes 2x2 minus x1 sine x2. Fine. So this 2x2 will be when we substitute x2 equal to 0. That means this becomes 0, this becomes 0. So we have a equal to this. So x dot is equal to 1 0 1 1. So this is your linearized. So this is your linearized approximate of your nonlinear system that was given around at this equilibrium point x1 equal to 0, x2 equal to 0. So with this A matrix, we can find out the eigenvalues. Lambda I minus A equal to 0. It gives us lambda 0 minus 1, lambda minus 1. Determinant is equal to 0, which gives us lambda minus 1 into lambda minus 1 square is equal to 0, which tells us the location of poles is 1 and 1. So with these eigenvalues, that's 1 and 1, that's repeated roots. Since these are positive repeated roots, we can say the equilibrium point that's actually corresponding to the corresponding to the origin of the system will be having the system will be unstable. Fine. You can also find out you can find out other eigenvalues of the system as well, and corresponding to those eigenvalues you can determine whether your system is stable or not. So in that indirect method, the stability of a nonlinear system around an equilibrium point is essentially the same as those of the linear approximate. It will help us, but in only finding out the local stability, not the global stability of the system. We can only say whether a system with a particular equilibrium point of a system is stable or not. In another case, what we have is the Lyapunov direct method. Uh, the Lyapunov direct method is the more general of the two. It's a powerful tool that can be used for analyzing the stability of nonlinear system. We can use to determine whether a linear system is stable as well using this method, but we are generally using it for the nonlinear system. So the generalization of the energy concept associated with mechanical systems, that is actually the motion pattern of the mechanical systems, is what is the focus here. It states that the motion of a mechanical system is stable uh, so this method dealing with the energy concept states that A motion of a mechanical system will be stable if the total mechanical energy associated with this system will be decreasing all the time. Hence, in the direct method, the idea is to basically construct an energy function, or what is also known as a Lyapunov function. So in this case, we'll be constructing an energy function, or what is also known as a for the system, and examining this function. It will be a time varying function, uh, and it's known as a Lyapunov function, and we denote this by v of x. Fine. So you have the Lyapunov indirect method, where we go for the linearization process. We approximate the system for various equilibrium points around different equilibrium points and examine each and every stability around each and every stable equilibrium point of the system. While as in the second case, that's the Lyapunov direct method, we define the stability of a system in terms of its energy function. A system can be said to be stable if its total mechanical energy decreases all the time. So now we'll be having different uh, stability criteria that actually we have somewhat studied for linear systems as well. We'll be looking into the asymptotic stability of the system. We'll be looking into the exponential stability of the system. We'll also be looking at the global asymptotic stability of the system. So Lyapunov's can tell us whether our system is stable or unstable using this energy function concept. Fine. So we'll start with the Lyapunov direct method with defining. We'll put forth different definitions of the Lyapunov direct method for analyzing the stability of the system, be it asymptotic stability, be it exponential stability, or the global stability. Fine. Lyapunov indirect method, that was only confined to the local stability of the system, but the Lyapunov direct method, will consider the global stability of the system. So that's all for today.